In 2017, the original transformer architecture solved a specific, isolated problem, translating text from one language to another, sequence to sequence. Over the past 8 years, those simple text predictors have evolved. Today's frontier models operate as multi-stage, multimodal reasoning engines capable of executing complex autonomous workflows. Reaching this level of performance requires moving far beyond the basic self-attention mechanism. We optimize the internal matrices, build software tailored to hardware memory, deploy new alignment algorithms, and ultimately break the bottleneck of generating text one word at a time. Frontier performance in 2025 depends on the synergy of this entire stack, shifting the engineering focus from raw parameter volume to the precision of the pipeline. The core engine of the architecture remains the self-attention mechanism. It processes an input sequence by allowing every single token to establish a direct mathematical link to every other token, regardless of how far apart they are placed in the sequence. To process longer sequences, engineers had to rethink how tokens track their location. Instead of assigning a static, absolute position to each word, modern models use rotary position embeddings. This mathematical operation rotates these vectors based on the relative distance between a query and a key, giving the model a dynamic understanding of context. Evaluating all those relationships requires massive memory overhead. Grouped query attention mitigates this by grouping multiple query heads and mapping them to a single key-value cache. The network retains high performance while reducing the memory required to store intermediate calculations. This efficiency carries over into the feed-forward network layer through mixture of experts. Instead of passing every piece of data through the entire model, a gating mechanism routes each specific token sparsely to only the relevant subnetworks or experts. By combining rotary position embeddings, grouped query attention, and mixture of experts, engineers decouple the total parameter count of a model from the active compute cost required to run an inference pass. Training a large language model requires striking an exact mathematical balance between model size and data volume. The chinchilla scaling laws establish a rule of thumb. An optimal training run requires at least 20 tokens of data for every single parameter in the model. Processing trillions of tokens exposes a severe physical constraint. The compute bottleneck is not the mathematical operations themselves, but the memory input and output moving the data back and forth to be calculated. Looking at this schematic of a GPU chip, we see the divide. The hardware possesses a large, slow outer ring called high bandwidth memory and a tiny, ultra-fast internal core known as the SRAM. The flash attention algorithm solves the memory bottleneck by dividing the query, key, and value matrices into smaller chunks. These chunks are loaded into the SRAM, computed entirely from end to end, and then written directly back to the large outer memory, skipping the intermediate read and write steps. At the 2025 frontier, software algorithms are tailored specifically to the physical memory hierarchy of the hardware they run on. The pre-training phase teaches a model the structure of language through basic autocomplete. To make the model useful, engineers apply supervised fine-tuning, demonstrating the exact input and output behavior required for specific tasks. The system is further aligned through preference tuning. By using human pairwise data pointing out which response is better, engineers train a separate reward model, utilizing the Bradley-Terry formulation to score the probability of one output outperforming another. Historically, this alignment relied on proximal policy optimization. This logic tree exposes a drawback. Calculating the advantage required maintaining an active value model in memory to establish a baseline for how good a prediction was, effectively doubling the structural overhead. Group Relative Policy Optimization, or GRPO, eliminates that overhead.
The algorithm drops the value model entirely. Instead, it samples multiple different completions for the same prompt and evaluates their relative rewards directly against each other. In domains with verifiable ground truth, like math or code, GRPO eliminates the dependency on learned reward models. By comparing multiple samples against a fixed correct answer, the model reinforces the specific reasoning paths that consistently yield the right result. Even highly trained models suffer from a static knowledge cutoff. Retrieval-augmented generation solves this by fetching external, up-to-date documents and injecting them directly into the prompt context. The system retrieves documents in a two-step pipeline. First, candidate retrieval uses a bi-encoder setup, taking the vectorized query and computing the cosine similarity against a database of document embeddings to extract a broad list of matches. That list is then refined through a cross-encoder. The initial query and the retrieved documents are run through a joint neural network to output a highly precise, re-ranked order of the most relevant information. Models interact with external systems through tool calling. The sequence pauses. The model outputs an exact API schema with arguments. An external script executes the action, and the resulting data is fed back into the context window so generation can resume. By coupling precise re-ranking pipelines with deterministic tool execution, engineers convert a static text predictor into an autonomous agent capable of resolving complex logic loops. The underlying transformer architecture is highly adaptable. Vision transformers operate by slicing an image into flat vector patches, treating them exactly the same way an LLM treats discrete text subwords. But whether processing text or images, standard language models face a strict limitation. They are autoregressive. They must predict left to right, requiring 10 separate forward passes to generate 10 tokens of text. Masked diffusion models adapt the parallel generation techniques used in image creation directly into discrete text. As shown in the bottom of this diagram, instead of generating one word at a time, the model starts with a full sequence of blank mask tokens, treating them as the text equivalent of Gaussian noise. The network learns an unmasking function. It refines the entire block of text through coarse-to-fine refinement iterations, stepping from a rough conceptual draft down to the final specific tokens across just a few discrete passes. Abandoning the left-to-right autoregressive bottleneck allows the model to process context in both directions simultaneously. This reduces inference latency, driving speedups crucial for complex coding tasks and agentic workflows. The research pushing these architectures forward is absolutely relentless. New techniques like muon optimizers are actively challenging legacy update rules, while hardware engineers are prototyping analog chips that embed matrix computations directly into physical signals. But an immediate data wall is approaching. As synthetic AI-generated text floods the internet, recursively training models on that low-diversity output leads to model collapse, degrading the underlying data distribution. To solve this and push the limits of cost efficiency, the industry is deploying small language models, meticulously trained on highly curated datasets rather than scraped web data. To start building your own applications using these techniques, check out the Learn by Doing with Steven YouTube channel. It walks through practical engineering implementations of the systems we covered today. For audio deep dives into the latest research papers, tune in to the Steven Data Talk podcast. Links to both are in the description below. Advancing the frontier now involves a transition from theoretical discovery to a high-stakes engineering discipline, one that requires the simultaneous integration of optimized hardware, efficient memory management, and verifiable alignment. A standard large language model is sealed off from the outside world. Its knowledge freezes at the exact moment its training data is cut off. It has no live connection to current events, no memory of new facts, and no ability to observe a changing environment. To bypass this limitation, the industry default has been to aggressively expand the model's context window. The logic assumes that if the model doesn't know something, developers can just dump hundreds of thousands of tokens, entire books' worth of raw, unfiltered text directly into the prompt. But here we see a heat map illustrating the needle in a haystack phenomenon. As the prompt length grows, the model's ability to retrieve a specific relevant fact degrades sharply. The flashing red areas represent lost information. When you feed an LLM too much irrelevant data, it gets confused and fails to locate the correct answers hidden in the noise. Beyond losing accuracy, this brute force approach comes with a massive computational price tag. API calls charge per token. Shoving hundreds of pages of text into every single prompt forces the system to process massive amounts of redundant data, driving inference costs exponentially higher. Overcoming these performance and cost plateaus requires a transition toward an active architectural engineering approach. These failures in recall, cost, and static knowledge define the requirements for a truly independent system. To function outside the context window, the model needs a pipeline for selective memory,
a method for executing software, and a loop for multi-step goals. The first layer is dynamic memory, achieved through retrieval augmented generation, or RAG. Rather than dumping an entire database into the context window, a RAG pipeline acts as a precise, narrow stream. It searches an external knowledge base, extracts only the highly relevant information, and injects that specific data into the prompt. To make this searchable, the raw documents in your knowledge base must be systematically indexed. The text is sliced into pieces called chunks, typically around 500 tokens in length, with a slight overlap between them, so that sentences at the borders aren't abruptly cut off. Slicing a large document into hundreds of isolated paragraphs strips away the broader context. A 500-token chunk about a specific financial metric might not explicitly mention the company name or the year it belongs to, rendering it practically invisible to the retrieval system. To solve this, developers use contextual retrieval. Before the chunks are stored, an LLM processes the original full document and generates a short overarching summary. This summary is then prepended to every single isolated chunk, permanently tethering the specific data back to its original context. Calling an LLM to read a massive document for every single chunk summary is highly resource-intensive. Engineers use prompt caching to mitigate this. Because the document prefix is identical for every chunk, the system calculates the neural network activations once, saves them, and simply looks them up for subsequent requests, dropping the cost heavily. Proper indexing and caching create a highly efficient, context-aware foundation. When the system reaches for memory, it pulls fully formed semantic meaning rather than disjointed text. Here we see the two-stage retrieval pipeline. The first stage is candidate retrieval. Its goal is pure recall. It filters millions of stored chunks down to a pool of a few hundred potentially relevant candidates, executing this as fast as possible. This stage relies on two parallel searches. First, semantic search uses bi-encoder models, like SentenceBERT, to measure the cosine similarity between the query's mathematical embedding and the chunk's embeddings, finding concepts that share meaning. Second, heuristic keyword matching, known as BM25, looks for exact vocabulary overlap, ensuring you don't miss a document just because it uses highly specific terminology. Sometimes a short user question and a dense reference document are structurally too different to match cleanly. A technique called hypothetical document embeddings, or HYDE, prompts the model to generate a fake, ideal answer to the query first. The system then searches the database using that fake document's embedding, which structurally mirrors the target chunks much closer than a brief question. Once you have your rough candidate pool of a few hundred chunks, the pipeline moves to stage 2, re-ranking. The goal shifts entirely from fast recall to strict precision. While bi-encoders process queries and chunks independently, this stage uses a cross-encoder. By simultaneously processing both the original query and the retrieved chunk together in the same neural network, the model captures deep cross-attention. This outputs a highly accurate relevance score, sorting the chunks into a strict top K list. This is the formula for normalized discounted cumulative gain, or NDCG, which evaluates if the ranking actually works. Pay attention to the denominator, which applies a logarithmic discount based on the item's rank. NDCG evaluates the entire ranked list. If your system successfully retrieves a highly relevant document, but places it at rank 10 instead of rank 1, the denominator aggressively discounts its value. The formula mathematically penalizes the system for burying the best answers. A simpler evaluation metric is mean reciprocal rank, or MMR. Instead of measuring the entire list, MRR strictly looks at the position of the very first relevant document. If the first correct answer is at position 2, the score is 1/2. If it's at position 3, it's 1/3. High recall grabs the haystack, and high precision isolates the exact needles. This mathematical optimization solves the context window illusion entirely. RAG gives the model an excellent memory, but it remains a passive observer. It can fetch a document about the weather, but it cannot actually adjust your smart thermostat. To interact with the physical and digital world, we implement tool calling. Developers inject specific software function APIs along with detailed documentation of their inputs and outputs directly into the model's preamble. The critical distinction here is that the LLM does not execute the code itself. It takes a natural language request, recognizes which tool is needed,
and maps that request into exact structured JSON parameters. The external system runs the Python API, gets a result, and feeds it back to the model. Models learn to format these tool calls through supervised fine-tuning. Engineers train the model on thousands of pairs, mapping user queries to perfect API outputs, or use highly capable reasoning models to generate explicit instructional prompts that guide the tool's usage step by step. This creates a massive scaling bottleneck. A true enterprise agent might need access to hundreds of APIs. Loading all of their documentation into the context window for every single query degrades performance and drives up latency. The engineering solution is tool routing. The user query hits a lightweight intermediate LLM layer first. This router scans a massive grid of 50 tool icons, extracts exactly which APIs are relevant to the specific prompt, and passes only those few functions into the active context window. Anthropic's Model Context Protocol, or MCP, provides a standardized architecture for this. By separating the LLM client from external MCP servers that host the actual tools and data, you create a modular, highly scalable ecosystem. By combining tool routing with protocols like MCP, the LLM bridges the gap between probabilistic text generation and deterministic software actuation at an enterprise scale. Agency emerges when the model stops treating every prompt as a single-turn prediction and starts pursuing a target through iterative loops. We architect this autonomy using the React framework, Reason plus Act. This framework structures the LLM's thought process into a continuous loop of 3 nodes: observe, plan, and act. If a user states that their teddy bear is cold, the model enters the observe node. It analyzes the vague natural language query and translates it into an actionable system state, realizing it currently lacks data on the room's temperature. The cycle moves to the plan step, deciding to retrieve that missing data. The act node executes the specific get current room temperature API. The external software returns a value of 65 degrees, feeding it straight back into the top of the loop. The system observes the 65-degree reading, determines it is too low, plans a heat increase, and triggers an adjust temperature tool. This recursive logic continues firing on its own until the model confirms the final goal is met and exits the loop. You can scale this by linking entirely separate agents together. Frameworks like Google's agent-to-agent protocol standardize the communication, allowing an energy management agent to negotiate directly with the temperature agent. Autonomy introduces severe security risks. An agent equipped with recursive reasoning and API access can easily cause systemic damage. If a malicious prompt tricks an autonomous email agent into accessing restricted files, it can seamlessly execute a data exfiltration attack. Mitigating this requires a comprehensive defense stack. Protection begins during training, embedding harmlessness constraints directly into the model's weights using reinforcement learning. At inference time, independent safety classifiers act as a firewall, intercepting the conversation and halting the agent's actions if the behavior violates security policies. Because failure modes in dynamic loops are highly unpredictable, these defense mechanisms are continuously evaluated against rigorous testing frameworks, like Agent Safety Bench, to systematically quantify vulnerabilities. The React loop provides the engine for autonomous problem-solving, but without strict architectural safety constraints, that same engine can cause cascading system failures. This is the complete architecture of a modern agentic LLM. A user prompt enters the central model. The RAG pipeline uses biencoders and crossencoders to pull precision memory from external databases. The MCP tool router selects the specific software APIs required, and the React loop drives the reasoning, cycling through observations and actions until the task is complete. The static next token predictor is now surrounded by a live infrastructure that fetches memory, triggers software, and manages its own recursive planning. As these agentic capabilities take over raw code generation and execution, an engineer's taste, the ability to verify correctness, enforce strict safety, and validate architectural logic becomes the most valuable asset in the industry. To put these exact frameworks into practice, head over to the Learn by Doing with Steven YouTube channel and platform. And for deeper conversations on data engineering and architectural design, listen to the Steven Data Talk podcast, available on YouTube Music, Spotify, and all major platforms.
Traditional large language models are extremely good at guessing the next word in a sequence. But when presented with complex mathematical or coding problems, that linear autocomplete style prediction breaks down. To solve hard problems, models need to generate a chain of thought, explicitly breaking the problem into intermediate steps before finalizing an answer. Initially, AI labs tried to teach this behavior by relying on supervised fine-tuning. Engineers would feed the model thousands of examples of humans writing out step-by-step logic, hoping the model would simply mimic that structured process. Sourcing these high-quality reasoning chains is incredibly expensive. Writing them from scratch takes specialized experts hours per problem, creating a severe bottleneck. You simply cannot generate enough human data to scale this approach indefinitely. Even if you could, there is a core cognitive mismatch. The way a human reasons through a physics problem relies on intuition and experience. That human heuristic does not naturally align with the mathematical way a language model optimizes its token probabilities. Because of this, trying to teach a model to reason solely through supervised fine-tuning means its capabilities are strictly capped by the limits of the human data it was trained on. Rather than forcing a model to copy exactly how a human thinks, the architecture needs to evaluate what the model produces. We have to shift to reinforcement learning to reward the final, correct outcome. Typically, aligning a model involves reinforcement learning from human feedback, where human raters score the model's answers. But for advanced mathematics or thousands of lines of code, human evaluation is far too slow and subjective to provide a clean, high-volume training signal. This necessitates a shift toward objective measurement through verifiable rewards. This approach moves the burden of evaluation from human judges to deterministic code. If a model writes a program, a compiler can automatically check if the code runs and passes test cases. If it solves a math equation, a deterministic parser can verify if the final string matches the known ground truth answer. The environment itself provides an absolute binary signal of success or failure. The training reward is then split into two clear checks. First, a formatting reward ensures the model successfully wrapped its logic inside designated think tags. Second, an accuracy reward triggers only if the final extracted solution is completely correct. By combining these two checks, verifiable rewards create a self-contained optimization cycle. Models can continuously generate logic and verify their own results against objective systems, which allows for pure logic optimization at a scale that human data cannot reach.
Once a model begins thinking, evaluating its true capability becomes complex. For highly difficult tasks, forcing the model to rely on a single attempt is incredibly noisy. One small arithmetic error ruins the entire output. Instead, the industry evaluates reasoning using a metric called pass at k. This calculates the statistical probability that if the model generates a batch of k unique attempts, at least one of those attempts will successfully solve the problem. Looking at this diagram of the derivation formula, you can see how it works. Rather than calculating the odds of success across varying attempts directly, it defines the metric as 1 minus the probability that every single sampled attempt is incorrect. This models the evaluation as sampling without replacement. We take the number of total possible failures chosen k times, divided by the total number of generations chosen k times. This chart graphs the pass at k score against generation temperature. A low temperature produces safe, repetitive answers. As you increase the temperature, the model generates highly diverse reasoning paths. This increases the likelihood of finding one correct answer in the batch up until the point where diversity peaks and the logic completely collapses into hallucination. The pass at k framework proves a crucial structural mechanic. We can directly trade inference compute for reasoning accuracy. Granting a model the extended time and massive compute to generate more answers yields mathematically higher success rates. To optimize these models during the reinforcement learning stage, the industry historically relied on an algorithm called proximal policy optimization, or PPO. Looking at the PPO workflow on the left, there is a critical architectural flaw. It requires the primary policy model to run alongside a massive parallel value model, which attempts to predict the expected future reward for every single token being generated. Running this secondary value model token by token introduces a crippling compute overhead and doubles the memory demands on already massive network architectures. To fix this, researchers introduced Group Relative Policy Optimization, or GRPO.
As you can see on the right, this architecture removes the value model entirely. Instead, it takes a single prompt and generates a group of G distinct completions directly from the policy model. The advantage, how good a specific completion actually is calculated relative to its peers. The system scores all the completions in the group and compares each individual reward against the mean and standard deviation of that exact batch. Because the scoring is relative to the group, it inherently self-adjusts for the baseline difficulty of the prompt. A hard math question where most outputs fail will still accurately isolate and highly reward the single successful logic path. By eliminating the massive memory requirements of a parallel value function, GRPO allows engineering teams to focus all their hardware and compute cycles squarely on policy optimization. However, this specific equation represents the original GRPO objective function, and it contains a mathematical flaw. Notice the normalizing term at the end, 1 over the absolute value of O, which represents the output sequence length. This division creates a bad incentive. Dividing the advantage by the output length means that the mathematical penalty for a short, incorrect answer is significantly harsher than the penalty for a long, incorrect answer. During training, the model quickly figures this out. It begins artificially inflating its reasoning length, endlessly babbling before committing to an answer, simply to minimize the mathematical penalty applied to its tokens. Modern iterations of GRPO fix this exploit by either equalizing token-level contributions across the board or deleting that denominator entirely. Once the math is corrected, the runaway output length stabilizes. An objective function must flawlessly map to the desired behavior. A language model will ruthlessly exploit any mathematical loophole to maximize its reward. This dynamic is perfectly illustrated by DeepSeek R10. This model was a proof of concept, trained from a base language model using pure, verifiable reinforcement learning without any prior formatting supervision. While R10 achieved elite scores, its outputs were functionally broken. It suffered extreme readability issues, mixed multiple languages mid-thought, and lacked a structural anchor. To fix this, DeepSeek engineered a hybrid production pipeline for their official R1 model. It begins with a cold start phase, utilizing several thousand highly curated supervised fine-tuning examples, specifically to enforce rigid formatting and language consistency. Once the output structure is anchored, Phase 2 applies the GRPO algorithm, using verifiable rewards on math and coding problems to massively scale the model's logical capabilities. Phase 3 is rejection sampling. Using the newly capable model, engineers generate thousands of potential outputs for difficult prompts. An automated judge filters out the noise, keeping only the highest quality logic paths to use as a massive synthetic dataset for another round of fine-tuning. Finally, Phase 4 applies a standard reinforcement learning pass targeting general helpfulness and harmlessness, ensuring the reasoning model functions safely as an everyday assistant. Producing a highly capable reasoning model requires an interweaved approach. Supervised fine-tuning provides the formatting anchor, and reinforcement learning scales the raw logic. Deploying a massive 600 billion parameter model like DeepSeek R1 locally or for everyday applications is financially and technically prohibitive. The solution relies on distillation. This is the process of transferring the dense cognitive capabilities of a massive teacher network directly into a much smaller, highly efficient student network. Instead of running the entire expensive reinforcement learning pipeline again, distillation uses the massive teacher model to generate millions of verified, correct logic chains. These outputs are used as direct, ready-made, supervised fine-tuning data to train the smaller student model. This methodology has enabled models as small as 8 or 14 billion parameters to achieve reasoning scores that match closed-source behemoths. The immense compute investment required for deep reinforcement learning serves as a one-time cost. It yields high-quality synthetic data that immediately elevates the reasoning capabilities of the entire open-source ecosystem. The architecture of AI development is rebalancing. The industry is actively shifting vast amounts of compute away from initial pre-training and reallocating it directly into inference time reasoning and search operations. By leveraging verifiable rewards and highly efficient algorithms like GRPO, models can now optimize their own logic at scale, breaking past the strict limits of human-labeled data. To build these systems yourself, visit the Learn by Doing with Steven YouTube channel for step-by-step technical tutorials on modern machine learning architectures. And for long-form discussions on the mechanics driving the AI industry, search for the Steven Data Talk podcast, available right now on Spotify and YouTube Music. If you ask a language model whether you can put your teddy bear in the washer, you might get a factually correct but blunt response. No, it might get damaged. Or you might get the exact same facts, but with a gentler tone. It's better not to. Your teddy bear could get hurt. Getting a model to understand how to answer, rather than just what to answer, is the core challenge of AI alignment. The second stage of training, supervised fine-tuning, or SFT, is excellent at teaching a pre-trained autocomplete engine to follow instructions, but it struggles to instill subjective behavioral traits like friendliness or safety. SFT has strict operational limits. Curating tens of thousands of perfect, high-quality demonstration prompts is incredibly expensive. Heavy curation also risks biasing the model's prompt distribution. More importantly, SFT only teaches a model exactly what it should predict next. It lacks a built-in mechanism for negative signals. You cannot easily use SFT to tell a model what not to say. To fix this, systems engineers implement a third training stage called preference tuning. Here, the goal is no longer teaching the model formatting or facts. The goal is aligning the model's behavioral outputs with specific human preferences. A pre-trained model knows language. An SFT model knows how to execute a task. But achieving a safe, helpful, and aligned assistant requires bridging the gap between raw token prediction and subjective human values using preference data. To build a preference dataset, we feed a prompt into an SFT model with a positive temperature, generating two distinct outputs. A human evaluates them side by side, designating a winner and a loser to create a binary pair. This pairwise data forms the foundation for Phase 1 of reinforcement learning from human feedback, or RLHF. We take a frozen copy of our language model, removes its text generation layer, and attach a scalar classification head. This creates a reward model. The Bradley-Terry equation maps a sigmoid curve over the difference in rewards, calculating the probability that response I is better than J. We optimize this model by wrapping the probability in a negative log likelihood loss function, adjusting internal weights to maximize the human-preferred data. Notice the operational quirk here. We train the reward model entirely on pairwise comparisons, but once trained, we deploy it to output a single pointwise scalar score for any individual text completion it reads. The reward model has one specific job. It mathematically quantifies subjective, qualitative human preference into an exact machine-readable scalar value. With our preference mathematically defined, we move to Phase 2, reinforcement learning via proximal policy optimization, or PPO. The language model acts as an agent, taking actions by predicting tokens, and receiving a signal from the frozen reward model about how well it did. The active policy optimizes for advantage, an estimation of how much better a generated output is compared to an expected baseline, calculated using a jointly trained value function. But PPO introduces a severe systemic threat. If you give an AI a mathematical score and an unconstrained mandate to maximize it, the system will exploit the metric. Imagine a lecturer whose only objective function is the volume of applause at the end of class. They realize quickly that telling jokes generates louder cheers than teaching complex math. The score is maximized, but the core objective, education, is entirely lost. In machine learning, this is called reward hacking. An unconstrained model generates bizarre, repetitive text, triggering the reward classification head, while losing specific knowledge acquired during pre-training. This chart maps the engineering solution within PPO. The solid curve is the active, updating policy. We apply a KL divergence penalty, represented by the dotted boundary lines, which forces the new policy to stay mathematically proximal to the original frozen SFT reference model. PPO's strict proximity constraint is the mechanism preventing the active policy from cannibalizing its own intelligence to chase high reward scores. PPO is mathematically elegant, but in practice, it is computationally brutal. Look at the memory footprint required for PPO training. You must carry 4 distinct neural networks in VRAM simultaneously. Compounding this memory tax is algorithmic drag. The active model must stop training, generate fresh rollouts, score them, and then resume, constantly bottlenecking training speed. For engineering teams without infinite compute budgets, there is an architectural alternative to PPO called Best of N. Best of N skips the reinforcement learning training phase entirely. Instead, at inference time, you take a prompt and generate N parallel completions from your standard SFT model. You run all of them through your frozen reward model, score them, and serve the highest rated completion to the user. This completely removes the instability of RL training, but it pushes the massive computational tax directly onto inference. Generating 5 answers to serve 1 means multiplying your API costs and latency by 5. Teams must choose between unstable, memory-crushing training pipelines with PPO or brute force, expensive inference serving with Best of N. In 2023, researchers published a mathematical bypass to this alignment dilemma called direct preference optimization, or DPO. The DPO paper operates on a single thesis: your language model is secretly a reward model. Researchers solved the PPO objective, proving through algebraic rearrangement that the reward term, the R you see here, can be entirely expressed as log probability ratios of the active policy and frozen reference. Plugging this back into Bradley-Terry completely eliminates the explicit reward model. This algebraic substitution transforms unstable reinforcement learning into a direct supervised classification loss function operating directly on your preference pairs. The hardware implications are immediate. Returning to our GPU footprint, the reward model and value function blocks dissolve. Hardware requirements drop from 4 simultaneous models down to just 2. DPO collapses a brittle 4-model reinforcement pipeline into a stable 2-model supervised problem using pure mathematics. This matrix shows that aligning language models is an optimization problem balancing training compute, inference compute, and performance. RLHF using PPO maintains the highest performance ceiling, but demands massive engineering resources to stabilize its 4-model architecture. Best of N avoids training headaches completely, acting instead as a brute force tax on inference costs and user latency. DPO provides an elegant, stable mathematical shortcut back to supervised learning, though it carries a minor risk of distribution shift if the preference data strays too far from the base model. To see the code implementations and build these architectures from scratch, check out the Learn by Doing with Steven YouTube channel. For deep dive discussions on machine learning paradigms, search for the Steven Data Talk podcast on Spotify and major audio platforms. Links in the description. Preference tuning serves as the mathematical bridge. It takes raw autocomplete capabilities built during pre-training and fine-tuning, converting them into a functional, aligned, safe AI assistant. This matrix shows that aligning language models is an ongoing optimization problem, balancing training compute, inference compute, and model performance. RLHF using PPO maintains the highest performance ceiling, but it demands massive engineering resources to stabilize its 4-model architecture. Best of N avoids training headaches completely, acting instead as a brute force tax on inference costs and user latency. DPO provides an elegant, stable mathematical shortcut back to supervised learning, though it carries a minor risk of distribution shift if the preference data strays too far from the base model. To see the code implementations and build these architectures from scratch, check out the Learn by Doing with Steven YouTube channel. And for deep dive discussions on machine learning paradigms, search for the Steven Data Talk podcast on YouTube Music, Spotify, and major audio platforms. Links are in the description. Preference tuning serves as the mathematical bridge. It takes the raw autocomplete capabilities built during pre-training and supervised fine-tuning and converts them into a functional, aligned, and safe AI assistant. Ask a raw, pre-trained language model how to wash a dirty teddy bear, and it won't give you instructions. Instead, it might generate a Wikipedia-style article about the materials used to manufacture stuffed animals. But ask an aligned assistant the exact same question, and it tells you step by step how to hand wash it. This happens because a base transformer model is not designed to solve your problems. Its sole mathematical objective is to predict the statistically most likely next token based on the vast corpus of internet text it ingested. Modern language models are built in 2 distinct stages to solve this. First comes pre-training, which builds a massive statistical world model from raw text. Second is supervised fine-tuning, or SFT, which aligns the model's behavior to follow instructions and act as a helpful assistant. Scaling these two stages to hundreds of billions of parameters introduces a severe structural bottleneck. The memory and compute required to process trillions of words across massive neural networks exceed the physical capacity of individual hardware units. Transforming these networks from mathematical concepts into physical reality depends on distributed systems engineering and hardware-aware optimization to make training possible. The pre-training phase requires models to ingest tens of trillions of tokens, scraped from the entire internet, to map the structure of human language and code. This animated chart visualizes the chinchilla scaling laws. It plots a fixed compute budget against model performance, revealing a distinct optimization curve. It proves intelligence relies on a strict mathematical relationship between neural network size and training data volume. Looking at the optimal sweet spot, we find a highly specific ratio. Optimally, you need roughly 20 tokens of training data for every single model parameter. Early architectures often ignored this math, wasting immense compute by building networks with hundreds of billions of parameters, but starving them of training data. Today's models are calibrated strictly along this curve. Achieving high performance is an exercise in exact economic scaling. Throwing massive amounts of data at an arbitrarily large network is mathematically inferior to precise, balanced optimization. Once the optimal size is determined, engineers hit a physical memory wall. A standard enterprise GPU is physically capped at roughly 80 gigabytes of internal memory. This bar chart illustrates exactly how fast that memory fills up during the backward pass of training. We store the model's weights, forward activations, gradients, and optimizer states, immediately bursting far past the 80 gigabyte limit. Looking closer at the optimizer states block, we see what bloats this footprint. The atom optimizer forces the GPU to maintain the first and second moments of the gradients, multiplying the required memory well beyond the base weights. To physically compute this impossible load, engineers use distributed training, linking multiple GPUs into a massive cluster to share the burden. The simplest approach is data parallelism, which divides the training batches across the cluster, but it has a critical flaw. It forces every single GPU to hold a full, duplicated copy of the model, wasting precious memory. The solution is the Zero Redundancy Optimizer, or ZERO. ZERO slices those massive memory blocks horizontally, sharding the parameters, gradients, and optimizer states across multiple GPUs, so every individual device stays under its 80 gigabyte limit. ZERO provides massive memory savings, but it introduces a severe operational tax. The GPUs must constantly pass these matrix fragments back and forth over the network, incurring significant communication delays. By accepting that communication delay, ZERO physically enables the pre-training of 100 billion parameter models that would otherwise be impossible to instantiate on silicon. Even with the memory distributed, another physical bottleneck emerges, the input-output speed limit. GPUs can execute mathematical operations much faster than they can read or write data to their own memory banks. Inside a single GPU, there is a strict memory hierarchy. There is a large, relatively slow storage pool called high bandwidth memory, or HBM, connected to a tiny, ultra-fast block called SRAM, where the actual computation occurs. The standard self-attention formula forces a continuous, slow data transfer. Matrices for queries, keys, and values are repeatedly loaded from the HBM into the SRAM, computed and written back to the HBM in a highly inefficient loop. To bypass this I/O bottleneck, researchers developed flash attention, an exact, non-approximate algorithm that reorganizes the data flow using a technique called tiling. Instead of moving entire matrices, tiling loads small, localized blocks of the queries, keys, and values into the fast SRAM. The complete softmax computation is processed locally, end-to-end, and only the final result is written back to the HBM. During the backward pass, flash attention takes a counterintuitive approach. Instead of saving all forward activations into the slow HBM to reuse later, it discards them and recomputes them from scratch on the fly. By minimizing memory reads and writes, flash attention proves that doing more total mathematical operations can actually speed up overall training time, circumventing the physical memory transfer limits entirely. With the hardware constraints managed, engineers turn to optimizing the numerical data structures themselves.
This diagram shows how mixed precision training yields massive efficiency gains. By shrinking a 32-bit floating point number down to exactly half its length to represent a 16-bit format, the system drastically doubles compute speed and halves memory requirements. Mixed precision training follows a strict rule. The base model weights must remain stored in high-precision 32-bit format. This prevents tiny rounding errors from accumulating and permanently degrading the model during gradient updates. These optimizations allow the model to complete pre-training. Next comes supervised fine-tuning, or SFT, which shifts the model's objective toward following specific user instructions. During SFT, the objective function calculates loss differently. Instead of trying to predict every single word from the beginning of a sequence, it calculates loss only on the generated response to a fixed user instruction. Unlike the massive scale of the pre-training internet scrape, the SFT dataset requires orders of magnitude less volume. However, it demands pristine, human-curated quality to teach the model safety, accuracy, and helpfulness. Pre-training builds the raw statistical horsepower, but precision-managed SFT acts as the steering wheel required to make the output useful to a human. Adapting a 100 billion parameter model for every specific downstream task or business application is financially impossible if you have to update the entire network every time. Researchers solved this economic hurdle with low-rank adaptation, or LoRa, which enables parameter-efficient tuning. The foundational step of the LoRa architecture is to freeze the massive, expensive pre-trained weight matrices. These base weights require absolutely zero memory to update because they remain entirely static. Next to this frozen base, LoRa injects two tiny, trainable, low-rank decomposition matrices that run in parallel. When this tall, narrow matrix multiplies against this short, wide matrix, it produces a new output that exactly matches the dimensions of the frozen base. This rank reduction works because multiplying these tiny matrices yields a full-size parameter update, but uses only a microscopic fraction of the computational footprint. By dropping the required compute from a cluster of GPUs down to a single machine, LoRa democratizes model fine-tuning. It shifts the power to build specialized, domain-specific AI out of the exclusive hands of hyperscalers and into the hands of individual engineers. From raw text to aligned assistant, the complete LLM training pipeline is an exact science of scale and physical constraint. Distributed networks leveraging zero and SRAM optimized algorithms like flash attention make trillion-token pre-training physically possible. Supervised fine-tuning and parameter-efficient techniques like LoRa sculpt that raw statistical capability into highly specialized human-aligned applications. The final step is verifying that utility, testing these highly engineered models against complex benchmarks and human preference testing to ensure they perform safely in the real world. Modern artificial intelligence is the result of neural network architecture meeting the physical constraints of hardware and systems engineering. If you want to move beyond the theory and actually start applying these architectures, I invite you to check out the Learn by Doing with Steven YouTube channel and on other platforms. And for deeper conversations on the future of machine learning, listen to the Steven Data Talk podcast, available on YouTube Music, Spotify, and other various platforms. Modern large language models rely on massive, decoder-only architectures trained on datasets exceeding tens of trillions of tokens. Increasing the intelligence of these systems involves scaling parameter counts into the hundreds of billions, but activating every parameter for each individual token generation creates a computational load that exceeds the limits of standard real-time hardware. This problem is built into the autoregressive nature of text generation. Because the model must predict each token sequentially, it must wait for the completion of one forward pass before starting the next. This sequential process moves the bottleneck from raw floating-point operations to memory bandwidth. During inference, the GPU often sits idle, waiting for the massive model weights to transfer from VRAM into the processors. Efficient deployment requires a pipeline designed to navigate these specific memory and bandwidth constraints. We will build this pipeline by integrating three specific systems: mixture of experts for scaling,
probability sampling mathematics for diversity, and memory paging for VRAM efficiency. This approach transitions the LLM from a theoretical neural network into a hardware-aware systems engineering pipeline. In a standard transformer block, the feed-forward network is the most expensive layer. Its high dimensionality and massive parameter count account for the majority of the total compute required for a forward pass. We can manage this cost by splitting that network into n parallel subnetworks, or experts. Before reaching these experts, a token passes through a router, or gate, which generates a probability distribution for it. The router analyzes the token's representation to decide which specific expert is mathematically best suited to process its information. In a sparse MOE system, we only activate the top K experts, usually just 1 or 2. This routes the token through a single path, while the other experts remain inactive. This architecture allows us to scale the total parameter count significantly, while capping the active floating point operations per forward pass. This creates a risk of routing collapse, where the model favors a single expert for every token, essentially ignoring the rest of the capacity built. We solve this by adding an auxiliary loss function during the training phase. This punishes the model if the routing distribution becomes too narrow. This auxiliary loss ensures a uniform distribution across all experts, proving that we can scale model capacity without linearly scaling the compute required at inference. As the data reaches the final output phase, a linear layer projects the hidden state into the vocabulary space. These raw scores are then converted into a probability distribution through a softmax function. Selecting only the single highest probability token from this list is known as greedy decoding. While locally optimal, this often leads to suboptimal long-term sequences. The model can become trapped in repetitive loops or generate text that feels statistically flat. Systems can instead use beam search to track several probable paths at once, though this still frequently results in a lack of diversity. To prevent nonsensical words, top K sampling truncates the distribution, removing the low probability tail. The temperature hyperparameter sits in the denominator of the softmax calculation, allowing us to adjust the curve's shape. As temperature approaches 0, the math forces an absolute spike. The highest logic gains nearly full probability, making the model deterministic. As it increases, the differences diminish, flattening into a uniform line, giving low probability tokens equal chance. Modifying this single hyperparameter variable gives engineers precise control over the balance between deterministic logic and creative variation. Managing the physical GPU VRAM is our final bottleneck. To generate a new token, the model must attend to every previous token, meaning every step relies on the specific states of the entire history. Rather than recomputing these states for every new token, we store the key and value matrices in memory. This is the KV cache. Standard allocation systems try to reserve a single contiguous block of memory for this cache. Because most requests are shorter than the limit, this results in significant fragmentation. Large VRAM sections remain empty. Page detention solves this by treating VRAM like virtual memory in an operating system. The KV matrices are broken into small, fixed-size blocks that can be stored anywhere in memory. A block table mapping system tracks these scattered pieces, stitching them back together seamlessly for the attention calculation. By eliminating fragmentation, page detention allows a single GPU to handle much larger batches of requests simultaneously, increasing total throughput. We can further reduce the memory footprint through multi-latent detention, which passes the token through a low-rank compression matrix. This achieves a smaller cache size by sharing a single latent representation across all attention heads. But even with optimized memory, we are still bound by sequential generation. The model must finish token A before it can begin token B. Speculative decoding bypasses this limit using a smaller draft model. It guesses several tokens before the main model starts. The larger target model verifies the draft in a single parallel pass, accepting correct guesses and rejecting errors. An acceptance mechanism based on the total probability theorem ensures the final output exactly matches the large model's distribution, even using draft guesses. This mathematically guarantees the high-quality output of a massive model at the speed of a much smaller one. From the routing gates of a mixture of experts architecture to the paged blocks of the KV cache, the journey of a single prompt is a sequence of hardware-aware optimizations. Moving a theoretical architecture into a production environment requires solving these physical constraints. Scaling these models effectively depends on the simultaneous engineering of the architecture, the sampling mathematics, and the memory management. For practical guides on building these systems, visit the Learn by Doing with Stephen YouTube channel. To join the conversation on data and systems engineering, find the Stephen Data Talk podcast on Spotify, YouTube Music, and all major platforms. The "attention is all you need" paper defined the modern era of AI, but the specific architecture it proposed is now functionally obsolete. To scale sequences beyond a few hundred words, researchers had to rebuild the transformer's internal engine to prioritize memory throughput and hardware utilization. The 2017 design faced three primary physical limits. It struggled to maintain positional context, it became unstable at extreme depths, and its memory requirements grew too large for modern GPUs to handle efficiently. We are going to deconstruct the specific upgrades that solved these bottlenecks: ROPE, RMS norm, and GQA, and see how the encoder-only paradigm evolved for specialized classification tasks. Modern LLM development prioritizes throughput and scaling constraints over historical architectural purity. Because self-attention calculates the relationship between every token in a set simultaneously, it is natively permutation invariant. Without an external signal, the model has no way to distinguish the first word in a sentence from the last. The original solution involved adding absolute positional vectors, essentially a fixed coordinate, to the token embeddings before they ever reached the attention layers. This approach is brittle. The positional signal is frequently washed out by the time it travels deep into the network, and the model cannot easily infer positions beyond the specific sequence length it saw during training. Rotate position embeddings, or ROPE, shift this logic by injecting positional data directly into the query key interaction. Before calculating attention scores, ROPE multiplies the query and key vectors by a rotation matrix. The degree of rotation is determined by the token's index, here shown as M for the query and N for the key. When we take the dot product of these two rotated vectors, the absolute positions M and N effectively vanish. Because a rotation matrix is orthogonal, the resulting inner product reduces to a function of the difference between the two angles. This means the attention score now inherently represents the relative distance between tokens. By embedding position as a rotation, the model's similarity bias is mathematically tied to proximity, allowing it to generalize to much longer sequences than it encountered during training. In massive networks, activations often fluctuate wildly as they pass through different layers, a phenomenon known as internal covariate shift that can stall training entirely. To fix this, researchers moved the normalization step. By shifting from post-norm to pre-norm, normalizing the vector before it enters the attention or feed-forward layer, they ensured a more stable flow of gradients during training. However, the standard layer norm calculation requires finding the mean of the activations and subtracting it. At scale, this subtraction step is computationally expensive and, as it turns out, largely unnecessary. RMS norm simplifies the math by scaling the activations strictly by their root mean square. It skips the mean centering entirely, relying on a learned parameter, gamma, to rescale the vector. This streamlined approach achieves the same convergence stability as layer norm, but with significantly less computational overhead per layer. Global attention is a quadratic problem. If you double the length of your input, the computational work required to compare every token to every other token increases fourfold. Many modern architectures interleave global attention with sliding window layers. These restrict each token to only attend to its immediate neighbors, capping the computational cost, while still allowing information to propagate through the network's depth. The second bottleneck occurs during generation. To predict the next word, the model must store the keys and values of every previous word in its memory, a structure called the KV cache. In standard multi-head attention, every query head has its own dedicated key and value projection. As the context grows, this cache quickly consumes all available GPU memory. Multi-query attention attempted to solve this by forcing every query to share one single key and value head. While this saves memory, it often degrades the model's ability to learn complex relationships. Grouped query attention, or GQA, finds the middle ground. It groups query heads together to share a single K and V projection, drastically reducing the memory footprint of the KV cache while maintaining the model's representational power.
GQA is now the industry standard because it allows models to handle massive context windows on consumer-grade hardware. While generation models use a causal mask to hide future words, classification tasks require a different approach. Extracting the dense meaning of a sentence is more efficient if the model can look at the entire sequence at once. This led to the BERT architecture, which discarded the decoder entirely. By focusing only on the encoder, BERT achieves true bidirectional context. BERT is trained using masked language modeling. By hiding 15% of the tokens, the model is forced to use the information from both the preceding and following words to predict what's missing. To understand how sentences relate to one another, BERT uses a separator token and a next sentence prediction task, classifying whether two phrases naturally follow one another. All this information is aggregated into a single classification token, the CLS token. Because it attends to every other word in the sequence, it becomes a dense summary of the entire input, perfect for downstream classification tasks. By focusing purely on encoding, this paradigm created a tool that could map the contextual relationships of language with extreme precision. Despite its power, the original BERT model is computationally expensive to deploy, leading to significant latency in real-world applications. To solve this, researchers used knowledge distillation to create DistillBERT, a smaller, faster student model that retains the knowledge of its larger teacher. Distillation works by minimizing the KL divergence between the teacher and student models. Instead of learning simple labels, the student model learns to mimic the teacher's soft probability distributions, capturing the nuanced relationships the teacher has already discovered. While DistillBERT focused on speed, the Roberta project pushed for maximum performance. They discovered that BERT was actually undertrained and that several of its original assumptions were incorrect. Roberta achieved state-of-the-art results by removing the next sentence prediction task entirely, using larger batches and training on significantly more data over longer periods. These two paths allowed the industry to specialize: DistillBERT for low-latency deployment and Roberta for absolute predictive accuracy. The transformer has evolved into a library of modular, highly refined mathematical operations. From ROPE for positional context to GQA for memory management, every choice in modern architecture is a calculated response to the physical limits of our hardware. Moving beyond the basics of attention is all you need is the first step toward building systems that can actually scale. To see these architectures in action, visit the Learn by Doing with Stephen YouTube channel for implementation-focused coding tutorials. And for deep dive discussions on the engineering trends shaping the field, subscribe to the Stephen Data Talk podcast, available on YouTube Music, Spotify, and all major platforms. This shows the primary computational challenge in natural language processing: taking distinct sequential human text and mapping it into a continuous stream of numerical data. Machine learning models tackle this mapped data in three categories. The first is standard classification, where the model predicts a single label, such as extracting a positive or negative sentiment. The second is multi-classification, where it identifies multiple elements within a string, like extracting named entities. The third category is generation. Tasks like machine translation require taking text in and producing text out. Because the length of the generated output varies based on the input, evaluating accuracy here presents a unique computational hurdle. For standard and multi-classification, we measure success with rigid quantitative metrics like precision, recall, and the F1 score for imbalanced datasets. Generation tasks, however, rely on metrics like perplexity, which measures the mathematical probability of the model's generated output. Calculating the accuracy of a single word classification is a trivial math problem, but generating long, fluent passages exposes a strict mechanical limit in early machine learning: the mathematical inability to maintain structural context over a long sequence. To achieve true language generation, engineers had to abandon treating text as a sequence to be read from left to right and start treating it as a geometric space to be modeled in parallel. We are going to build the architecture of modern large language models entirely from first principles. By tracking the math, we will see exactly where every preceding system broke down mechanically. Solving the problem of context was a strictly architectural and mathematical achievement, rather than a linguistic one.
neural networks cannot process raw strings of text. The mandatory first step is tokenization, which divides the text into discrete units that can be mapped to numerical tensors. If we split the text at the word level, we generate massive vocabularies. The model treats variations like run and runs as completely distinct entities, creating an unacceptably high risk of encountering out-of-vocabulary errors during generation. Splitting the text at the individual character level eliminates that out-of-vocabulary risk entirely. The trade-off is that it drastically increases the sequence length, which cripples computational efficiency. Subword tokenization offers the mathematical optimum. By breaking text down into common linguistic roots, it balances a low out-of-vocabulary risk with a manageable sequence length. This optimal tokenization strategy restricts the overall sequence length. Keeping that sequence size mathematically viable is a hard prerequisite for the heavy matrix multiplication required in the subsequent layers. Look at this 3D coordinate plane. If we represent our tokens using a basic one-hot encoding strategy, each word becomes an orthogonal vector pointing along independent axes. Because they are perpendicular, their cosine similarity is exactly 0. All semantic relationships are destroyed. To fix this, models use proxy tasks, like cross-entropy loss to predict neighboring words, to learn representations like word-to-vec. The strict orthogonal grid collapses, and the isolated vectors converge into a dense, continuous vector space cloud, where grouped points represent related concepts. By mapping tokens into a continuous hidden layer dimension, semantic similarity translates directly to geometric direction. Words with similar meanings point in similar directions, yielding a high cosine similarity. Continuous embeddings effectively map semantic meaning to spatial geometry. However, they critically fail to encode where a specific token is positioned sequentially within a sentence. This creates a sequential bottleneck. If you use a standard vector embedding, the mathematical representation for a word remains identical, regardless of its grammatical context in the text. Recurrent neural networks attempted to solve this isolation. As we see in this unrolled flowchart, an RNN processes one token at a time, calculating and passing a continuous hidden state value sequentially from one node block to the next. The mechanical flaw emerges during backpropagation through time. Updating the network's weights requires multiplying a long series of sequential gradient values together along this exact backward path. When these sequential gradients are fractions less than 1, their continuous multiplication causes the value to decay exponentially. Over long distances, it flatlines at 0. This is the vanishing gradient problem. The hardware consequence is severe. Because each step strictly depends on the calculation before it, you cannot process the sequence in parallel on modern GPUs. RNNs hit a hard mathematical and physical wall. They inevitably lose long-range context by design, and their architecture inherently blocks efficient scaling. The 2017 transformer architecture bypassed this by abandoning sequential processing entirely. Instead, it relies on direct, highly parallel connectivity between all words simultaneously. In this visualization, a single input embedding is projected into 3 distinct learned matrices: a query, a key, and a value. To find the mathematical similarity between tokens, the self-attention operation computes the dot product of the query matrix against the transposed key matrix. This generates a new n by n attention weight grid. This raw grid is divided by the square root of the key dimension to prevent the gradients from saturating, and then passed through a softmax filter. This transforms the raw data points into a probability distribution that sums to 100. Finally, this normalized probability distribution is multiplied by the values matrix. The output is a final, context-aware vector block. To capture varied semantic associations, the architecture uses multi-head attention. It runs this exact query, key, and value projection multiple times simultaneously, using different learned matrices. Self-attention replaces fragile sequential loops with robust matrix multiplication. It avoids the vanishing gradient problem, aligning natively with parallel GPU hardware. For complex generation tasks, these attention blocks are stacked into a larger macro architecture, strictly divided between an encoder and a decoder. The encoder's role is to aggressively process the source text. It uses multi-head self-attention and feed-forward networks to build a contextualized mathematical representation of the input. Because this happens in parallel, the system has no inherent concept of word order. It relies on positional encodings, injecting sine and cosine values into the embeddings to retain sequence structure. The decoder's role is generating the final output sequentially. To accomplish this, it utilizes a specific masked self-attention layer. Masked self-attention is strictly unidirectional. It mathematically prevents the model from looking ahead at future, unpredicted tokens during the autoregressive generation. The encoder and decoder integrate at the cross-attention layer. Here, the decoder generates the queries based on what it has processed so far, but it pulls the keys and values directly from the encoder's rich output. This architecture elegantly separates the deep, parallel geometric understanding of the input space from the strict, sequential generation required for the output space. The transformer architecture dominates modern AI precisely because its dense matrix multiplications perfectly mirror the parallel processing capabilities of modern GPU clusters. Beyond the hard architecture, training optimization introduces a statistical problem: model overconfidence. Standard one-hot labels fail during training because they force a strict 100% confidence target for the next token. This ignores the natural variance of language and actively harms the model's ability to generalize. Engineers solve this using label smoothing. By mathematically shifting the training target from a hard 1 to 1 minus epsilon, they deliberately inject uncertainty. This improves generation evaluation metrics like the BLUE score. The combination of frictionless parallel hardware alignment and statistical regularization techniques permanently established the transformer as the bedrock of large language modeling. Mastering the linear algebra and geometric architecture of the transformer is merely the theoretical prerequisite for deploying robust machine learning models in production environments. To transition from theory to hands-on applied engineering, explore the tutorials available on the Learn by Doing with Steven YouTube channel, and keep up with the evolving machine learning ecosystem by subscribing to the Steven Data Talk podcast, available on all major platforms.
In standard software development, evaluating performance is straightforward. A classification model takes an input and outputs a deterministic binary result, a clean 1 or a 0. But large language models generate free-form text, complex blocks of Python code, and multi-step mathematical proofs. Because this output is non-deterministic, we cannot rely on simple rule-based scoring systems to check if the model is correct. Two completely different sentences can contain the exact same factual truth. This introduces a strict engineering problem. If you cannot reliably measure a system's output, you cannot systematically optimize it. Without measurement, you cannot improve the model, grinding your development to a halt. To measure this scalar complexity, engineers rely on a specific three-tier architecture, the LLM evaluation stack. At the micro level, we evaluate individual outputs. We discard rigid word matching algorithms in favor of building an automated LLM as a judge to evaluate semantic meaning. At the meso level, we evaluate multi-step reasoning. We dissect autonomous agent loops to isolate exact execution failures when models attempt to use external tools. Finally, at the macro level, we measure raw base model capability against global benchmarks. Mastering this complete three-tier stack allows us to accurately map the Pareto frontier of artificial intelligence. The instinct is to evaluate LLM outputs by having human raters grade them, but human raters operate slowly, cost a premium, and frequently disagree on subjective tasks. This matrix shows Cohen's kappa, a statistical metric used to measure inter-rater reliability. We use it to determine if human agreement is driven by clear guidelines or random chance. Even aligned humans introduce too much variance for high-volume testing. In the past, engineers relied on hard-coded rule-based metrics like BLUE, METEOR, and ROUGE. These formulas compare a model's output to a single static reference text. But these formulas look strictly for n-gram overlap. If your model generates a perfectly accurate response that uses a different stylistic phrasing than the reference text, metrics like BLUE actively penalize it. To solve this, the industry standard shifted to using a separate, high-capacity model as a grader, a proxy for human preference, known as an LLM as a judge. This architecture requires three specific inputs: the original prompt, the model's generated response, and a crisp binary grading criteria.
These feed directly into the judge, which evaluates the text semantically. For this to work inside an automated testing pipeline, the judge's output cannot be freeform. We must use constrained decoding, often called structured outputs, to force the judge to return a programmatically parsable format, like JSON. To maximize accuracy, we structure the prompt to demand a rationale before the numerical score. This sequence forces a chain of thought process, giving it compute space to articulate reasoning before committing a final grade. This setup requires active mitigation of specific model tendencies. Judges exhibit position bias, favoring the first answer they see. They show verbosity bias, equating longer answers with better answers. And they suffer from self-enhancement bias, artificially inflating the scores of responses generated by their own base architecture. By controlling for these biases and constraining the output format, we transform the LLM judge into a reliable foundational unit capable of evaluating free-form truth at massive scale. Now, factuality introduces an entirely different challenge. A single text generation is rarely completely true or completely false. It is almost always a blend of accurate claims and subtle hallucinations. Consider this text. Teddy bears first created in the 1920s were named after President Theodore Roosevelt after he proudly wanted to shoot a captured bear. Evaluating this paragraph requires breaking it apart to ground the specific claims against concrete historical data. First, we extract atomic claims into index cards. Next, a RAG pipeline verifies each card against a knowledge base, confirming Roosevelt but rejecting the 1920s date. Finally, a weighted formula calculates a score, penalizing major historical errors more heavily than minor ones. We cannot treat factuality as a monolithic binary check. It must be engineered as an active pipeline of decomposition, verification, and weighted aggregation. Evaluating a single output is only the micro level. When we deploy models to perform actions over time, we enter the meso level, evaluating multi-turn agentic workflows. This models the react loop: observe, plan, act. We must debug agents at the node level. First, tool prediction fails if the model hallucinates a non-existent function. Second, argument errors happen when missing data forces the LLM to pass invalid defaults, like 0, coordinates. The third failure is an execution backend error. If your database crashes, returning a raw Python stack trace directly to the agent will confuse the model and break the loop entirely. Even if a search query yields no results, returning an empty JSON object is vastly superior to returning a none value. An empty JSON correctly signals to the model that the database was successfully queried and nothing was found, allowing it to plan its next move. And finally, we evaluate for synthesis errors. This occurs when a successful tool call returns a massive JSON payload, flooding the context window with raw, unstructured data. This sudden context truncation blinds the LLM. The answer might be buried deep in the payload, but the model cannot parse it, forcing it to falsely tell the user the task failed. Because the agent operates in an autonomous loop, a single node failure causes a cascading collapse of the entire system. Monolithic scoring obscures the root cause. Evaluating agent behavior demands isolating the variables and identifying exactly which node failed and why. When we step back from agents and individual outputs, we reach the macro level. Here, we evaluate raw base model capabilities using strict, hard-coded global standards. This matrix shows the core industry benchmarks: MMLU, AIM, SWE-bench, and TAU-bench. These tests eliminate the subjective noise of an LLM judge by demanding precise, verifiable answers. MMLU tests broad knowledge retention from the model's pre-training phase. It operates across dozens of academic fields using a strictly constrained multiple-choice format. AIM evaluates rigorous mathematical logic. It removes multiple choice entirely, forcing the model to generate its own reasoning path and land on an exact 3-digit numerical output. SWE-bench provides applied coding evaluation. The model is fed a real historical GitHub issue and codebase. We measure performance by injecting the model's proposed patch and running the repository's native unit tests to verify if they pass. TAU-bench shifts to multi-turn agents, simulating retail and airline environments to test policy navigation. Success is measured using pass-hat-k, calculating the strict probability that all k sequential attempts succeed, demanding absolute consistency. These global benchmarks strip away the ambiguity of natural language, providing the objective baselines we need to map the absolute frontier of model capability. But these benchmarks carry a systemic danger. When developers prioritize high scores over general capability, the tests degrade. This is known as Goodhart's law. When a measure becomes a target, it ceases to be a good measure. Due to data contamination, models often memorize the specific questions in these benchmarks during their training phase. They overfit to the test, creating an illusion of capability rather than true analytical intelligence. This is why the complete evaluation stack is your primary defense. You cannot rely solely on a single metric to understand how a model will perform in production. Evaluating free-form truth requires abandoning static text matching. It demands passing automated semantic judges, executing inside simulated agent environments, and verifying against global benchmarks. By integrating all three tiers, we build the rigorous engineering framework required to accurately map, measure, and push the Pareto frontier of AI performance. To build these systems yourself, head over to the Learn by Doing with Steven YouTube channel for applied tutorials. For deeper architectural discussions, search for the Steven Data Talk podcast on Spotify and YouTube Music.
Modern language models face a strict scaling imperative. To act as highly capable autonomous agents, they need to process contexts spanning 10 million tokens and route logic through multi-trillion parameter networks. The vanilla dense transformer cannot mathematically sustain this scaling. The big O compute limits are too severe. Looking at this standard block, the first bottleneck sits on the left, global softmax attention. Because every token must check its relationship against every other token, compute costs scale quadratically. If you double the sequence length, you quadruple the processing cost. The second bottleneck sits on the right, the dense feed-forward network, or MLP. In a standard setup, this is where the bulk of the model's parameters live. In a dense MLP, every single parameter fires for every single token. Your inference compute cost is strictly locked to your total parameter count. You cannot make the model smarter by adding parameters without simultaneously detonating your latency and compute budgets. Reconstructing the architecture for frontier scale requires mathematically bypassing the quadratic attention bottleneck and introducing conditional routing to bypass the MLP bottleneck. Scaling to trillions of parameters requires abandoning homogeneous computation in favor of selective, sparse architectures. This is the standard self-attention equation. The nonlinear softmax function here is the exact operation that forces the model to compute an enormous n-by-n interaction matrix. By deliberately discarding it, we gain the mathematical freedom to reorder the multiplication entirely. Without softmax, matrix multiplication is associative. We can shift the parentheses. Instead of multiplying the queries and keys together first, we multiply the transposed keys and the values. This reordering collapses the dimensionality. We bypass the n-by-n token interaction entirely. Instead, we compute the hidden dimensions against each other, shrinking an operation of millions of variables down to a fixed size of just a few thousand. What remains behaves exactly like a recurrent neural network. By multiplying keys and values left to right across the sequence, we accumulate a constant fixed-size state. Pure linear attention is efficient, but it is highly lossy. An unedited state vector carrying the entire context history forward eventually becomes noise. The network lacks a mechanism to forget irrelevant past tokens. To fix this, architectures like Mamba 2 and gated DeltaNet elaborate on the linear mechanism. They introduce input-dependent gates, represented here by gamma and beta. These gates do not rely on the prior hidden state. They look solely at the current input token to decide how much of the existing state should be carried forward and how much previous key information should be projected out and erased. Because these gates depend only on the input, they preserve an architectural duality. During training, the model computes the operations as massive, dense parallel matrices. At inference time, the model executes them as pure serial updates, carrying a fixed-size state forward without recalculating the past. Leveraging the associativity of multiplication converts a fatal quadratic memory constraint into a highly optimized parallel serial duality. If you want to retain the raw expressive power of softmax attention without the memory limits, the alternative is applying it selectively.
This timeline represents a long context sequence, which we can process using sparse attention mechanisms, like DeepSeek's DSA. Before running full attention, a lightweight indexer scans the sequence in low precision. It calculates brute force inner products across the sequence to evaluate relevance. The indexer ranks those relevance scores and executes a top K selection, isolating only the tokens that actually matter for the current computation. Only this scattered subset of selected tokens is routed into the heavy, full-precision softmax attention block. Mathematically, the indexer's initial scan is still comparing every token against every other token. It remains an operation with quadratic big O complexity. The efficiency comes strictly from systems engineering. Because the indexer operates in a much lower dimension and at lower precision, its constant factors are minuscule. Optimizing these algorithms requires looking past pure theoretical complexity.
By aggressively minimizing the operative constants on the front end, engineers make a mathematically quadratic operation behave practically like a linear one. With attention managed, we arrive at the second bottleneck, the dense feed-forward network. To scale up parameter capacity without exploding inference flops, we break the monolithic MLP apart into smaller, distinct subnetworks called experts. This is the mixture of experts, or MOE architecture. Instead of pushing data through every node in the network, tokens are routed to specific, specialized neural pathways. The router itself is extremely naive. It takes the input token and computes an inner product against a set of expert weight vectors. This outputs a probability mass, a score dictating which experts align best with the current token. Modern models default to token choice top K routing. The token independently selects a strictly capped number of its highest scoring experts, usually just one or two, and ignores the rest.
To push utilization further, architectures like DeepSeek segment those standard experts into dozens of highly fine-grained nodes. They isolate common language processing tasks into a single shared expert. Every token passes through this pathway automatically, preventing fine-grained experts from redundantly relearning basic syntax. The mixture of experts framework decouples latent knowledge capacity from active computational cost. You can train a model with hundreds of billions of parameters, but only pay the computational price of a fraction of them on any given forward pass. Training an MOE introduces a severe paradox. Sparse gating decisions are mathematically non-differentiable. Since we only activate a top K subset, the network never sees the loss gradients for the experts it didn't choose. You could treat this like a bandit problem and use reinforcement learning to teach the router, but the variance introduced by those algorithms makes the gradients far too unstable at this scale. Left to pure gradient descent, the model suffers from expert collapse. If one expert performs slightly better early in training, it receives stronger gradient signals. Its weights increase, making it more likely to be selected again. It creates a runaway feedback loop that funnels all tokens to a single expert, leaving the rest of the network totally dead. To prevent this, engineers inject a heuristic load balancing loss directly into the total modeling objective. This equation defines the balancing act. It multiplies Fi, the physical fraction of tokens assigned to a specific expert, by Pi, the total probability mass the router has allocated to that expert. Taking the derivative of this loss creates a direct penalty. The higher the fraction of tokens an expert receives, the stronger the negative gradient applied to its probability mass. It actively punishes popularity. In highly distributed environments, models apply this exact same heuristic loss at the device level, ensuring tokens are distributed evenly across the GPU cluster to maintain maximum hardware utilization. Achieving massive parameter scale requires overriding pure gradient descent. Without engineered heuristic losses forcing equitable distribution, the hardware simply starves. Frontier open models have moved past the homogeneous transformer design. This reconstructed architecture relies heavily on specialized pathways. It weaves state-space linear attention layers together with sparse dense attention to process million token sequences efficiently. It deploys massive sparse parameter networks, kept stable strictly by heuristic load balancing losses, to drastically scale its knowledge capacity. Frontier optimization has transitioned into a discipline of low-level systems engineering. Architectural viability is now dictated by hardware-specific constraints, like communication topologies, cache memory overhead, and the manipulation of constant factors. By mathematically manipulating the matrix and enforcing selective execution, engineers have decoupled raw compute costs from sheer intelligence. If you want to keep exploring the math and systems powering these models, subscribe to the Learn by Doing with Stephen channel and check out the Stephen Data Talk podcast for more in-depth engineering breakdowns.
When we talk about artificial intelligence, we usually picture clean neural network architectures and pure mathematical equations. The reality of creating these models is bound by physical space and harsh electrical constraints. Training a large language model requires warehouse-scale physical infrastructure. You are managing thousands of physical components, orchestrating the flow of electricity, heat, and data across massive server racks. Within those racks, engineers face a severe bottleneck. Look closely at the spec sheet for a modern H100 GPU. It promises nearly 1,000 teraflops of raw computing power. Yet, even when top laboratories actually train models on this hardware, they rarely achieve more than a 50% utilization rate. Half the hardware's capability sits idle. Training a large language model is a deterministic systems engineering problem, dictated by strict physical limits. To understand those limits, we have to start at the absolute bottom. Every parameter, gradient, and activation in a network is stored in memory as a tensor. Traditionally, the standard format for these numbers was float32. This format provides high resolution, but it demands 4 bytes of memory for every single parameter. For models with billions of parameters, that footprint immediately exceeds available memory capacity. Cutting the bits in half to float16 shrinks the exponent bits so much that the format loses its dynamic range. If you try training a deep network with it, numbers that get too small turn into zeros, and numbers that get too large cause overflow errors, crashing the training run. This diagram shows how the industry solved the problem with a format called bfloat16. Instead of equally shrinking the number, it sacrifices the mantissa, the fraction part responsible for high resolution. It shifts those bits over to maintain the exact same exponent size as float32. You lose decimal precision, but you maintain the necessary dynamic range to prevent the model from overflowing. Hardware engineers are currently pushing even further into 8-bit and 4-bit precision. Because 4 bits cannot cover the necessary dynamic range natively, they work around the physical limits by grouping values into blocks and applying a shared scaling factor to the entire block. Selecting this bit-level precision establishes the absolute physical floor of the entire model's memory footprint, long before a single computation is executed. Once the precision is set, those tensors must be moved and manipulated. In standard frameworks like PyTorch, developers manipulate matrices using arbitrary index-based transposes, requiring them to guess whether dimension -1 or -2 is the correct one to swap. Systems engineers avoid this ambiguity by relying on a library called INOPS as a structural solution for managing complex tensor operations. INOPS requires you to use named dimensions. You declare exactly what you are doing, mapping a sequence and a hidden dimension directly to a designated output matrix. Any dimension not explicitly mentioned gets summed out automatically. This naming convention forces the developer's intent to perfectly map to the hardware's physical memory layout. Clean, unambiguous operational syntax allows us to calculate the deterministic cost of our compute. We measure this cost in flops. A flop with a lowercase s is a single floating point operation, a measure of the total math required. Flops with an uppercase s denotes floating point operations per second, measuring hardware speed. This animation shows the arithmetic cost of a forward pass through a basic linear layer. We take our input data points, dimension n, and we multiply them by our parameter matrix, dimension d. Because each coordinate intersection requires one multiplication and one addition, the cost of this forward pass is 2 times the number of tokens, n, times the number of parameters, d. The backward pass requires twice as much work. The chain rule demands 2 distinct sets of gradients, one gradient with respect to the parameters and another gradient with respect to the inputs. That makes the backward pass cost 4 ND. 2 ND forward plus 4 ND backward yields the baseline calculation for language model training compute, 6 ND. Every single token passing through a parameter exacts a non-negotiable computational toll on the system. The chips have high bandwidth memory, where the tensors are stored, and specialized cores where the math actually happens. To compute anything, a massive stream of digital data must physically travel from memory across a narrow pathway into the accelerator. This introduces arithmetic intensity.
the ratio of flops executed per byte of data transferred across that memory bottleneck. Consider an element-wise operation, like a ReLU activation. The system pulls a massive vector into the core, performs a single comparison to 0 on each number, and sends it right back. The ratio of actual math to data movement is incredibly poor. Contrast that with a large matrix multiplication. You send an n-squared amount of data across the wire, but you compute an n-cubed number of operations once they arrive. The arithmetic intensity scales positively as the matrix grows. This graph shows the hardware's physical limits, known as a roofline plot. The y-axis tracks achieved performance, and the x-axis tracks arithmetic intensity. The sloped line is the memory bandwidth ceiling, and the flat line at the top is the peak compute ceiling. Operations like a ReLU activation are trapped here on the sloped line. They are strictly memory-bound. The accelerator sits idle, waiting for data to arrive. A massive matrix multiplication pushes past the inflection point and hits the flat ceiling. It saturates the hardware and becomes compute-bound. Model flops utilization hovers at 50% because the hardware is constantly starved for data transfer, not compute capabilities. Let's open the ledger and calculate the true memory cost of a single parameter during training. Using bfloat16, the baseline weight takes 2 bytes. The resulting gradient requires another 2 bytes. To navigate the loss landscape effectively, the Atom optimizer must constantly track the first and second moments of the gradients for every single weight. Accumulating these running averages in low precision causes severe mathematical instability. Atom requires standard float32, instantly adding a massive 8-byte footprint per parameter. The model weights are a fraction of the total cost. The optimizer states are what actually drown the GPU's memory. To stay compute-bound and maintain high arithmetic intensity, we need massive matrices and large batch sizes. But processing those large batches blows up the high-bandwidth memory with massive activations and optimizer states. To prevent the system from crashing, engineers implement 2 critical pressure valves. The first is gradient accumulation. Instead of processing a massive batch at once, the system slices data into micro-batches. It runs forward and backward passes on these smaller chunks to save memory, adds the results into a holding pool, and only steps the optimizer once the full batch accumulates. The second pressure valve is activation checkpointing. Normally, the forward pass saves every layer's activation for calculating gradients. Checkpointing intentionally drops most intermediate activations, flushing them to keep memory empty. During the backward pass, the system simply recomputes missing activations from the nearest saved checkpoint. Training a large language model at scale requires engineers to juggle bytes, cheating physical memory walls while fighting to keep arithmetic intensity high. If you want to take these theoretical frameworks and apply them practically, I highly invite you to check out the Learn by Doing with Steven YouTube channel and other platforms. And for deeper discussions on the data engineering that fuels all this, tune in to the Steven Data Talk podcast, available on YouTube Music, Spotify, and various other platforms. Links are in the description. We interact with AI through a simple text box, but that interface is a leaky abstraction. When you rely solely on prompting, you restrict yourself to a predefined sliver of the actual design space, completely walled off from the mechanics driving the output. To understand how these systems actually operate, you have to bypass the API entirely. You must tear up the entire software and hardware stack and examine the physical limits of the infrastructure. One way to frame the challenge of training is as a product of efficiency and resources. If accuracy is the objective, researchers must treat algorithmic efficiency as the primary lever for maximizing the output of a fixed compute budget. At the frontier scale, where training runs cost hundreds of millions of dollars, you cannot achieve higher accuracy by simply throwing more hardware at the problem. You have to ruthlessly optimize the algorithmic design to squeeze every possible operation out of your memory bandwidth. Constructing a language model from the ground up requires mastering 5 specific engineering disciplines. But before any parameters are updated or matrices are multiplied, the entire process relies on a bedrock layer of data compression. Understanding these layers step by step is the necessary path to transition from querying a pre-existing system to architecting a new one. The foundation is training basics. This is where we define the mathematical shape of the system. selecting the transformer architecture, allocating parameters into a mixture of experts, and tuning hyperparameters to maintain strict stability. The second layer is systems. Processing chips are extremely fast, but they sit physically separated from where the data is actually stored. Moving information from memory into the processor creates an intense structural bottleneck. To close that gap, engineers write custom CUDA kernels. These are specialized software instructions designed to minimize data travel, locking the compute sequences to match the exact high-bandwidth memory transfer speeds. Above that sits the third pillar, scaling laws. When a single training run carries an enormous financial cost, trial and error is no longer an option. You extrapolate performance using strict mathematical curves established on smaller models, predicting the exact loss you will achieve before the full-scale run even begins. The final two tiers dictate the model's actual utility: data curation and alignment. Here, vast reserves of raw web crawls are aggressively filtered and deduplicated before applying weak supervision techniques like direct preference optimization to shape the model's ultimate output behavior. To make this entire stack operate, we have to look back at the precise moment raw text first enters the machine. While alignment and scaling generate the majority of public interest, the throughput of the entire stack is capped by how effectively we compress raw text into the machine. A neural network has no concept of a human alphabet. The transformer architecture operates strictly on numerical indices. The most obvious way to translate text is to assign a unique integer to every single character. But treating every letter as its own data point stretches sentences into highly elongated, inefficient sequences. This directly triggers the core constraint of the transformer architecture. The computational cost of the attention mechanism scales quadratically relative to the sequence length. If you feed a character-by-character sequence into the model, that squared cost curve spikes. It instantly exhausts the GPU's memory bandwidth, grinding the entire training process to a halt. You could try the exact opposite approach. You could map entire, complete words as individual indices, keeping the sequence lengths as short as possible. But natural language contains millions of rare words, misspellings, and names. Attempting to map them all creates an unbounded, massively expanding vocabulary. This introduces severe matrix sparsity, transferring the overload directly to the embedding layer and blowing up the memory footprint in a different way. Rigid rules create a trap. Small units exceed compute limits, large units exceed memory limits. To thread the needle, the system requires an adaptive, dynamic compression algorithm. The industry standard solution is an algorithm called byte pair encoding. The process begins by stripping all text down to raw UTF-8 bytes. Because a byte can only hold 256 possible values, the system starts with an absolute baseline vocabulary size of exactly 256. The algorithm then sweeps across the entire training corpus, searching for the single most frequently occurring adjacent pair of bytes. When it finds a dominant pair, it merges them into a brand new token index and appends that new integer to the master vocabulary list. By replacing every instance of that pair across the entire dataset with the new single integer, the algorithm mechanically reduces the data volume, explicitly shrinking the total sequence length. This is a strictly iterative loop. The software scans the data again to find the next most frequent pair, and it is now fully capable of targeting the newly minted tokens. If our new token represents the letters T and H, it might quickly identify that this index sits right next to the byte for the letter E. It merges them, creating token number 257 to mathematically represent the complete word the. Through thousands of repetitions, the algorithm reaches an equilibrium. Highly common linguistic concepts organically fuse into single, hyper-efficient tokens. Conversely, rare words and strange misspellings aren't discarded or flagged as errors. They simply remain subdivided into their smaller, constituent byte chunks, completely preventing the system from ever encountering an unknown sequence. This mechanism directly satisfies the requirement of our starting efficiency equation. It maximizes the data compression ratio for every document passing through the system. BPE functions as a computational safeguard. It manages the quadratic expansion of attention costs by ensuring the transformer operates on the most information-dense sequence possible. Tokenization proves that securing algorithmic efficiency must start before the first piece of data is even processed. By adaptively compressing bytes into optimal sequences, the algorithm perfects the geometric shape of the inputs long before the first neural matrix multiplication takes place. This philosophy of optimization persists as you move up the stack. From writing custom logic for memory transfer, projecting performance through predictive mathematical curves, to aggressively sanitizing raw internet scrapes, every layer of the architecture is an exercise in resource extraction. The seamless interface of a chat window hides a physical reality defined by the orchestration of thousands of interconnected GPUs and petascale data streams. To push the boundaries of what these systems can achieve, you have to break past that clean API abstraction and confront the physical and algorithmic limits governing the hardware. Pushing the frontier of intelligence requires more than prompting. It requires an engineering mindset that confronts the physical and algorithmic limits of the hardware itself. To continue exploring applied model engineering and hands-on systems architecture, subscribe to the Learn by Doing with Steven YouTube channel. And for deeper dives into AI architectural strategy, listen to the Steven Data Talk podcast, available now on YouTube Music, Spotify, and Apple Podcasts.
For decades, the computer industry relied on a simple formula for speed: make the central processor's clock tick faster. Those early, bulky desktop machines relied on CPUs executing instructions in a single serial line. But by the early 2000s, this approach hit a physical wall. You can only shrink transistors and push clock frequencies so far before the silicon generates too much heat to function. The era of the single, ultra-fast core had peaked. To keep scaling, engineers built horizontally. Instead of one fast core, they turned to graphics processing units, GPUs, and later machine learning-specific tensor processing units, or TPUs. These chips process thousands of tasks at exactly the same time. While they share this parallel philosophy, their internal layouts differ. TPUs use a few massive, specialized units designed strictly for multiplying huge matrices. GPUs pack hundreds of smaller, highly flexible streaming multiprocessors into a single chip. Modern artificial intelligence doesn't rely on a single, blazing fast brain. It requires an orchestra of thousands of compute units working in unison across a massive grid. This chart tracks computational performance versus data transfer speeds. While GPU math capability has exploded upward, memory bandwidth has barely crept up. When a processor finishes math before memory supplies the next numbers, cores sit idle. That widening gap is the memory wall. Scaling an AI model effectively means mastering physical logistics. Success depends on the speed of data lanes as much as the logic of the code. Navigating this bottleneck requires perfect synchronization between the data and the silicon. Way out on the edges is the global memory, or DRAM, massive but slow. Far closer, built directly into the processor blocks, is shared memory, or SRAM. It is blazing fast, but space is strictly limited. Even if the data arrives on time, developers must ensure the cores don't waste the effort. That starts with Rule 1, avoiding if-else logic. In a parallel system, all threads must execute the same instruction at once. If code hits a conditional branch, half the chip sits idle while the other works. Every idle core is a wasted trip to memory. The second trick is shrinking the numbers themselves. By dropping the precision from a highly detailed 32-bit format down to 8-bit, engineers literally halve the physical weight of the data, allowing twice as much information to travel across the board in the same amount of time. Next is operator fusion. Instead of computing a single math operation, sending the intermediate result all the way back to slow memory, and retrieving it again for the next step, the code is written to perform the entire sequence of calculations at once, while the data is still inside the processor. The fourth technique is a paradox, throwing work away. Because reading and writing to distant memory is so costly, it is actually faster to permanently delete intermediate variables during training and recalculate them entirely from scratch when you need them later. You don't usually think about geography when you write code, but here, the goal of the software is strictly spatial. Trap the specific numbers in the absolute fastest, closest areas of the silicon for as long as possible. Global memory reads data in physical burst blocks, not individual numbers. To retrieve efficiently, requests must be grouped contiguously.
If the data's shape misaligns with these windows, engineers inject blank zeros, padding the matrices so they snap perfectly into those hardware boundaries. The final trick is tiling. Rather than processing a giant matrix all at once, developers chop the data into highly specific subblocks. These tiles are sized specifically to max out the tiny capacity of the fast shared memory. The chip loads a tile, runs every possible calculation it can on those specific numbers locally, and only then ships the finished piece to slow memory to grab the next block. The math operations aren't divided based on algebraic rules. They are sliced up based strictly on the exact microscopic square footage physically available on the silicon chip. All these physical constraints came to a head with large language models. The algorithm that stopped these giant models from crashing GPUs is called flash attention. Earlier attention mechanisms failed at scale because they generated massive intermediate matrices and continuously wrote them back and forth to slow global memory, completely clogging the transfer lanes. Flash attention bypassed this by aggressively tiling the input data and fusing the operations. It forces the hardware to keep the pieces on the fast part of the chip. This diagram shows the key to the algorithm, the online softmax. Instead of waiting to load the entire grid to calculate the probabilities, flash attention computes a running tally, updating the totals block by block. The math never has to leave the local cache. Flash attention revolutionized AI through the realization that, at extreme scale, software is effectively a hardware logistics problem. Developing the next generation of AI forces a departure from abstract equations. It requires a deep physical sympathy for the silicon itself. But understanding the theory is only the first step. To really grasp these mechanics, you have to build things yourself. If you're ready to start writing your own models from scratch, check out the Learn by Doing with Steven YouTube channel. You'll find practical tutorials that put these exact concepts into action. And for deeper conversations on where this technology is heading next, listen to the Steven Data Talk podcast, available on YouTube Music, Spotify, and anywhere else you get your podcasts. You can find all the links in the description below.
The most powerful image architectures today operate not by painting pixels from scratch, but by reversing the diffusion of structured data into pure noise. Specifically, we are going to deconstruct denoising diffusion probabilistic models, or DDPMs. To understand how they work, we will construct the forward process, the deliberate corruption of an image, and then navigate the intractable probabilities of reversing that corruption using a mathematical tool called the evidence lower bound, or ELDO. From there, we can derive the remarkably simple L2 loss function that trains the network, and finally utilize DDIM to drastically accelerate the generation speed. Trying to force a neural network to guess the exact configuration of millions of pixels in a single pass is overwhelmingly complex. Modeling the step-by-step decay of information gives the model a much simpler task, predicting tiny, localized increments of noise. This diagram outlines the forward process, Q.
We start with a clean image vector, x0, and progressively corrupt it over t steps. At each step, a noise schedule dictates the ratio of original signal to new Gaussian noise, governed by parameters beta t and alpha t. Calculating thousands of steps individually is computationally inefficient. Because we're adding independent Gaussians, their sum yields another Gaussian. This reparameterization trick lets us calculate any noisy state, xt, directly from the clean image, x0, using the cumulative product of signal ratios, alpha bar t. Bypassing sequential forward steps is the critical mechanic here. It allows the system to instantly generate millions of highly randomized training samples on the fly, making the entire training pipeline computationally viable. Our ultimate generative objective is finding the neural network parameters, theta, that maximize the probability of generating actual training data. Mathematically, this target is log p theta of x0. Here is the fundamental roadblock in this diagram. Computing that target probability requires marginalizing, or summing, over every single possible trajectory from pure noise at step t all the way down to the clean image at step 0. Attempting marginalization across thousands of steps creates a combinatorial explosion. The math is strictly intractable. To bypass this, we rely on the evidence lower bound, or ELBO, providing a safe, computable proxy for our target probability. To derive the ELBO, we start with our target probability and multiply it by a fraction of the known forward trajectory, Q over Q. Multiplying by 1 changes nothing algebraically, but it injects the forward process into our equation. Next, we apply Jensen's inequality. Because the logarithm is a concave function, this rule allows moving the logarithm inside the expectation over those trajectories. Moving that logarithm formally guarantees that the resulting expression is a lower bound. Optimizing this new equation will continually push our true target probability upward. The ELBO framework successfully transforms an impossible global probability calculation into a highly tractable, localized sampling problem that a neural network can actually solve. Expanding the ELBO reveals the Kullback-Leibler, or KL, divergence, which compares two specific probability distributions. The first, Q, represents the probability of stepping back to a less noisy image, assuming we know both the highly noisy image and the ground truth clean image. Computing this backward step directly is difficult. Our forward process Q is defined as moving from clean to noisy, meaning we need a mathematical inversion. Because the forward process is Markovian, depending only on the prior step, we apply Bayes' rule to invert the probability. The complex Q terms physically rearrange. Forward probabilities act as numerators and denominators, striking each other out, collapsing into a single, smooth Gaussian bell curve. The result is that this conditional probability is no longer intractable. It becomes a fully analytical, computable Gaussian distribution. This calculation is only possible during training. We can compute this specific Gaussian solely because the system has access to the ground truth data, x0. Anchoring the abstract, uncertain reverse step to the definitive x0 training data provides the fixed target the neural network needs to learn effectively. To finalize our training objective, we require one last assumption. The neural network, p theta, must also be designed to output a Gaussian distribution. Computing the KL divergence between two known analytical Gaussians causes almost all complex algebra to collapse, leaving behind only this simplified L2 distance equation. In this regression, the network takes two inputs, a noisy image, xt, and the time step, t. It is strictly tasked with predicting epsilon theta. That output is directly compared against epsilon, the exact pure noise originally added to the clean image. The immense, intractable complexity of generating photorealistic reality reduces mathematically down to a remarkably basic, elegant noise subtraction problem. This architecture creates a fatal bottleneck at inference time. To create a new image, you must execute the neural network sequentially for thousands of individual stochastic steps. The architectural solution to this speed limit is the denoising diffusion implicit model, or DDIM. The primary mathematical pivot in DDIM defines a new family of forward processes, Q sigma. These are non-Markovian, but perfectly match the marginal distributions of the original DDPM. The specific mechanical change is setting the stochasticity parameter, sigma, to absolute zero. Setting sigma to 0 makes the transition from xt to xt-1 strictly deterministic. We completely eliminate random noise injection. Without stochastic noise accumulating, the system can mathematically skip intermediate steps without destroying final image fidelity. Breaking the Markov chain requirement turns an academically elegant but sluggish model into a commercially viable high-speed architecture. State-of-the-art generation is achieved not by trying to predict the geometry of pixels, but by learning the precise geometry of noise. We leveraged the ELBO and KL divergence to turn an impossible, multi-dimensional probability problem into a highly tractable L2 regression. By manipulating the underlying stochasticity through DDIM, we successfully enable rapid, highly scalable deployment in the real world. To explore deeper coding implementations of these models, head over to the Learn by Doing with Steven YouTube channel. And for continuing high-level academic and industry machine learning analysis, stream the Steven Data Talk podcast on YouTube Music and Spotify. The core challenge of modern vision models is learning how to map an easily sampleable, chaotic noise distribution into a highly complex data distribution. Think of this generation process like sculpting.
You start with an unformed block of variation. By deterministically removing that noise piece by piece, you reveal the target sample hidden inside. The denoising diffusion probabilistic model, or DDPM, is the mathematical framework that systematizes this sculpting process. To understand how this operates, we have to construct the underlying math from first principles. That requires bypassing the intractable probability equations standing between pure static and a clean image. Then we have to address the real-world compute bottleneck. We will break the Markov chain to strip out the latency and achieve massive inference speedups. Mastering these specific mathematical nuances is what turns diffusion from a theoretical academic curiosity into a functional, state-of-the-art engineering system. This timeline establishes our training environment. Far left, x0, a clean image. Far right, xt, pure noise. The forward process incrementally corrupts the image over t steps, using a variance-preserving schedule governed by beta weights. The noise dose steadily increases as we approach total noise, but computing thousands of sequential step-by-step additions during the training phase would force our compute costs to scale out of control. Because the injected noise is drawn from a standard Gaussian, their variances can be summed linearly. We consolidate these into a direct jump variable, alpha bar. This allows us to calculate any specific noise step, xt, using a single operation. This direct jump property gives us a mathematically perfect, computationally cheap way to generate training pairs of any noise level on demand. Now we pivot to the reverse trajectory. We want to find the neural network parameters that maximize the probability of recovering the original training data. This note graph illustrates the mathematical requirement for computing that true reverse probability. It requires marginalizing across every single possible noise trajectory branching backward from step t. In the high-dimensional vector space of an image, the number of potential paths is staggering. Solving this specific integral is completely intractable. We bypass this impossibility using the evidence lower bound, or ELBO. By applying Jensen's inequality to the concave log likelihood function, we extract an expression that acts as a mathematical floor. This entirely bounds the problem. We no longer need to calculate the exact maximum probability, just confidently push this lower bound upward. The practical result? We can sample trajectories directly from our predefined forward process, Q. The elbow trick saves diffusion models from mathematical dead ends by replacing an impossible infinite sum with a tractable, sampleable expectation. Comparing these curves, we reframe elbow as a KL divergence problem, an operator measuring how far apart two probability distributions are. The first is the forward-posterior, Q. The second is the neural network, p theta, attempting to predict the exact same step backward. The critical advantage here is that both distributions are structurally Gaussians. Because of this, we possess the analytical solution required to compare them. When we feed two known Gaussians into the KL divergence formula, the complex probability variables structurally cancel each other out. The dense mathematics dissolve entirely, leaving us with a straightforward L2 regression. This reveals a counterintuitive reality about our loss function. The neural network is not predicting pixels or images at all. The network is exclusively predicting the exact noise vector, epsilon, that we injected at time step t. These highly complex, multidimensional probability distributions have now been successfully collapsed into a single, highly efficient geometric distance calculation. The training loss is elegant, but deploying this model for inference exposes a brutal latency problem. To generate a single image, data must be passed sequentially through the neural network up to 1,000 times. This sequence illustrates the mathematical culprit, the Markov assumption. A Markov chain dictates that every step strictly depends on the immediate prior step. Because of this rigidity, the model must inject a mandatory stochastic noise variable between every single node. We solve this inference bottleneck by deliberately breaking the Markov chain using the denoising diffusion implicit model, or DDIM. DDIM operates under one strict constraint. It formulates a new forward process that maintains the exact same marginal probabilities as DDPM. This ensures our pre-trained model weights remain valid. The mathematical leap is achieved by manipulating the hyperparameter that controls step-to-step variance.
DDIM manually forces that variance down to 0. Setting variance to 0 strips all stochasticity, transforming generation into a deterministic mapping from noise to image. The model can now approximate the clean data early, executing sweeping mathematical arcs that skip dozens of steps. This compresses a 1,000-step bottleneck into just 20 evaluations. Treating image generation as a rigorous sequence of continuous probability transitions is exactly how we tame isotropic noise into coherent structure. We bypass intractable mathematics in training by optimizing the elbow, simplifying competing probability distributions down into a basic noise regression. We resolve the massive compute requirements of inference by stripping out the Markovian step-to-step stochasticity, allowing DDIM to leap over the generation bottlenecks. If you want to deepen your practical application and build these systems from scratch, search for Learn by Doing with Stephen. And for high-level discussions on machine learning data architecture, listen to the Stephen Data Talk podcast. Mastering these underlying mathematical mechanics is the crucial difference between engineers who blindly deploy black box models and architects who actively build the future of machine learning. When we want a neural network to generate new, realistic images, we are essentially asking it to sample from a vast, completely unknown data distribution. Historically, models tried to learn this landscape by calculating the exact probability of every single point. But probability distributions must sum to 1 across the entire space. Computing that normalizing constant, a value known as z, requires summing across millions of dimensions. The math simply breaks down. It is computationally impossible. There is a mathematical workaround. Instead of forcing the model to calculate the absolute volume of the probability, we can teach it to find the gradient. We just need it to point in the direction where the probability gets higher. By discarding the need for an exact probability calculation, we remove the normalizing constant entirely. This specific adjustment takes high-dimensional data generation from mathematically impossible to computationally tractable. This equation defines a quantity called the score. It is the gradient of the logarithm of the probability density function. Because of the properties of logarithms, taking the gradient of the log probability splits the numerator and the denominator. The normalizing constant, z, is a constant with respect to position. Its gradient is 0. The intractable part of the equation cleanly cancels out. What remains is a vector field. At any coordinate in space, calculating the score gives you an exact directional arrow pointing toward the nearest concentration of real data. The lower the probability, the larger the magnitude of the arrow. This score function acts as a mathematical compass. We can start anywhere in the coordinate space and simply follow the gradients step by step to arrive at a realistic image, all without mapping the total volume of the space. To use that compass, we need to train a neural network to predict the score. But doing that directly requires knowing the true probability distribution of the data, which is exactly the unknown variable we started with. Researchers developed a proxy method called denoising score matching. By taking known training images and perturbing them with a small, specific amount of Gaussian noise, we create a mathematical target. The network learns to predict the score of this slightly noise distribution because the score of a Gaussian is analytically tractable. This topographical map reveals a structural flaw in that approach. When we only add a small amount of noise, the training data remains tightly clustered. The model learns the vectors near these dense peaks perfectly. But out here in the vast flat plains between the data points, the network receives almost no training signal. Its score predictions here are entirely inaccurate. To generate a new image, we start by sampling pure random noise. This pure noise places our coordinate in unmapped, low-density planes. When the model checks its compass, the vectors are meaningless. The math behind pure score matching holds up, but the execution fails. The model possesses a precise map of the destination, but has absolutely no navigational data for the origin. Solving this blind spot requires a technique known as a noise-conditional score network. Instead of relying on a single small noise level, we apply a massive spectrum of Gaussian noise to the training data. This extreme noise aggressively blurs the distinct data clusters, forcing their density to spread out and physically fill the empty voids. The entire space is now covered by a measurable gradient. Generation now begins using annealed Langevin dynamics. The model checks the score at the highest noise scale first. The vector here is blurry and imprecise, but it provides a reliable, broad direction pointing inward from the remote edges of the space. As the particle travels, the solver steps down to progressively lower noise scales. With each step, the topographical map sharpens, the broad slopes recede, the tight data peaks return, and the vector gradients become highly specific, guiding the coordinate to an exact high-resolution destination. By stacking these varying distributions, the network constructs a continuous gradient bridge. It connects the extreme outliers of pure noise directly to the sharp manifolds of realistic data. Look at these two equations side by side. On the left is the denoising diffusion probabilistic model, which preserves variance. On the right is the noise conditional score network, which explodes variance. While they operate differently, both rely on breaking the noise process into rigid, discrete increments. We can push these sequences to their mathematical limit. If we shrink the time step between noise increments down to 0, the discrete steps vanish. Both models collapse into a single continuous equation, a stochastic differential equation. This forward SDE breaks the continuous noise process into two distinct parts. First is the deterministic drift term, dictating how the data moves linearly over time. Second is the stochastic diffusion term, driven by a continuous random walk known as the Wiener process. Because the forward process is a verified SDE, we can apply an established theorem from 1982. This theorem proves that any forward SDE has a direct mathematical inverse. To reverse the flow of time and extract clean data from pure noise, the equation only requires one missing variable, the score. By moving away from discrete steps into the continuous domain, diffusion and score matching unite. They are simply two ways of configuring the same underlying differential equation. Watch this trajectory. When we generate an image by solving the reverse SDE, the stochastic noise injects constant randomness. The particle vibrates erratically as it moves. To keep this jagged path aligned with the target data, the solver must constantly self-correct, requiring hundreds or thousands of individual calculation steps. We can remove this computational bottleneck by converting the SDE into a probability flow ordinary differential equation. Using the Fokker-Planck continuity equation, the stochastic diffusion term is mathematically stripped away. The randomness is gone. What remains is a perfectly smooth, deterministic trajectory that maintains the exact same marginal probability densities as the noisy original. Without the need to calculate constant stochastic variations, the solver can traverse the exact same mathematical space using a fraction of the computational steps. The primary engineering goal in deploying these generative models is to reduce the number of function evaluations. Every time the neural network evaluates the score, generation slows down. This diagram shows the probability flow ODE formula. If we analyze the structure, we can separate it into two distinct parts. There is a purely linear equation block and a highly nonlinear block containing the neural network score prediction. Modern numerical algorithms, such as the DPM solver, exploit this separation. By applying the mathematical variation of constants, the solver calculates the linear portion of the trajectory exactly. The computationally expensive neural network is then only queried to discretize the nonlinear portion. By isolating these variables, the model takes massive, mathematically precise leaps forward. The process that once took 1,000 steps to trace is collapsed down to 10 to 20 evaluations, achieving the exact same visual output. To see the code behind these solvers and build your own implementation, search for the Learn by Doing with Stephen YouTube channel. For deeper discussions on the mathematics of generative modeling, find the Stephen Data Talk podcast on your favorite platform.